Hello everyone! Today I'll present RAGU, a modular, production-ready GraphRAG engine. While GraphRAG enhances large language models with structured knowledge, existing systems like LiteRAG construct knowledge graphs in a single extraction pass, producing noisy entities and brittle retrieval. We've built a system that separates extraction from consolidation through a 6-stage pipeline, yielding cleaner graphs and more reliable answers. Let me show you our tool in action. You can install RAGU with only one line via pip. Next section contains all the necessary imports and preparations. We import a little more modules that one user will need in order to show you the difference later. We also need to set up all the LLM client related things, as well as the modules for building and iterating a graph. Artifact extractor, search engine. We decided to use several pages of the UN website as a dataset for processing. Here they are. So how can you use our tool? It takes only one line to get a graph. As you can see, querying takes just a few lines of code. We have 3 different queries. Query 1 is a factual yes-no question. Query 2 requires retrieving a complete set of related entities and organizing them coherently. And query 3 is a multi-hop question. It is a complex query. So, query 1, for example, yes, space exploration is regulated by international law. So you see, the system is designed for simplicity, but this simplicity belies a sophisticated engineering underneath. RAGU processes documents through 6 configurable stages. Let us follow them. First, we have chunking. There are 3 chunk strategies: simple chunker for fixed size overlapping chunks, semantic text chunker for embedding base points, and smart semantic chunker with cross-encoder re-ranking. Here we'll use only simple chunker, because the text we will be processing for the demo are quite simple and small. We got 146 chunks. Then we come to the critical extraction phase. We support both single-stage and 2-stage extraction. Our recommended 2-stage approach extracts and validates entities first, then constrains relation extraction to the identified entity set. This prevents spurious entity-relation mismatches and sharpens extraction precision. All extractions follow the neural schema. You can see entity types and relation types if you want, with optional in-context learning using semantic, BM25 or hybrid retrieval strategies. Here you can see extraction in action on a chunk from our UN dataset. Now let's examine why 2-stage extraction matters. The notebook demonstrates both strategies side by side on the same text chunk. Here it is. So, with single stage, here we turn off this tab of validation. So, with single stage extraction, we see 6 entities and 4 relations, one of which is inspirates here, which is not actually in the list of entity types. So now contrast this with the 2-stage extraction. We turn on in-context learning, and we got 6 entities and 7 relations. You see, the 2-stage process forced the model to reconsider its classifications. After extraction comes consolidation. The entity summarizer groups entities by name and type, applies dbscan to handle duplicate mentions and uses LLM summarization to consolidate descriptions. Relation summarizer follows the same pattern. This noise reduction step is critical. It produces a cleaner graph before community detection. We got entities, validated them, got relations, validated them. Only after that we got summarization, summarized communities, and got nodes and edges of the graph. The result is a knowledge graph that both structurally sound and semantically rich. We got 940 entities and 1,692 relations. The notebook exports a self-contained HTML file, knowledge graph visualization HTML. Let us look for it and download it. It is in your working directory. Here you can see nodes are color-coded by entity type using color palette. You can see organization nodes in one color, age in another, award in yet another. The legend on the right provides the entity type color mapping. In this build, we have 940 nodes and 1,692 edges. So you can zoom and move to see descriptions of nodes, entities, and their relations. And also we have a filter menu, which allows you to focus on specific entity types or explore particular communities. For example, I want to find all nodes from group event. Here they are. So now that we have a graph, we can start iterating it. Let's trace exactly how local search retrieves evidence and generates an answer. Here's a demonstration with a query about international law. First, the engine embeds the query using our embedding model. Here it is text embedding 3 small. And then the embedded query is compared against all entity embeddings in the graph, and we retrieve the top k most semantically similar entities, here top 5. And once we have the relevant entities, the system expands the retrieval context in 3 ways. First, here, it finds relations connected to these entities. We see how much 46 relations here. Second, it retrieves the original text chunks where these entities appear. We get 10 chunks, providing direct textual evidence. And third, it pulls community summaries that contextualize these entities within broader themes. Here we see 5 community reports. All this evidence, entities, relations, chunks, and community summaries, is assembled into a structured prompt. The LLM receives the original question plus this rich context and generates the final answer. You can see the result, well, here. The answer is evidence-based, specific, and properly grounded. Now let us take a look at a few search engines out there. RAGU provides 5 interchangeable search engines. Local search performs vector similarity entity retrieval, then expands to related relations and chunks. Naive search provides standard vector RAG as a baseline. Global search operates on LLM-rated community summarization for a top-down view. MixSearch executes multiple engines in parallel and ensembles their results. And we have Query Plan Engine. It is something we show apart from others. It handles complex queries through DAG decomposition. So let us compare them. Here we see each engine retrieves different evidence. local search using entities and relations, naive search uses chunks, and global search uses community insights. The choice depends on your query type and desired response depth. Now let's examine MixSearch, our ensemble search engine. Unlike other engines that rely on single retrieval strategy, MixSearch executes multiple child engines, here there are two, and combines their results. MixSearch shows the power of ensemble retrieval, but for truly complex questions, we have something even more sophisticated, the query planning engine. Here. The query plan engine decomposes complex queries into a directed acyclic graph of subqueries. It executes them in topological order, passing dependencies between steps. Our example query, who comprises the UN Secretariat and what are their respective responsibilities, is broken into two subqueries. The first identifies the entities, and the second builds on this knowledge. This multi-step reasoning produces more detailed, structured answers than single-pass retrieval. The planned query yields responses that are both longer and more logically organized, demonstrating deeper reasoning. In summary, RAGU is an engineering mature GraphRAG engine that separates extraction from consolidation. It delivers cleaner graphs, higher retrieval quality, and production-ready reliability. Thank you for your time.